Hello class, today we'll look at logarithmic equations and our approach is going to be in two folds. We're going to see how we transition from logarithmic to exponential, which shouldn't be any news to you, as we said in earlier videos that logs and exponents are inverses of each other. So one of the ways you might see a logarithmic equation is written in the form as you see in the first box. So in the first box, you have log A of x is equal to b. If I can arrive at that position, so one of the features here is that the coefficient has to be 1. All right, as long as I see this, I can switch easily from the log to an exponential. So over here, if I'm able to convert this, I get a to the b is equal to x. And what's going to happen is if you're able to switch from a logarithmic to an exponential, chances are you put yourself in a good position to solve for that value of x. In the other box, I'm missing an L over here, we see an equivalency over here. We are saying that the log of a of x is equal to the log of a of y. We are saying that, and again, one thing that needs to happen is that the coefficient on each side needs to be 1. This needs to be true, okay? If this is true, then we can extract the argument and say that x must be equal to y. And again, if you're able to do this, you should be able to find an opportunity to find the variable that you're looking for. So we're going to use these two boxes alongside our rules of logarithms and the properties of logarithms to kind of help us. Because as you see in box B, I need to have a log on the left and a log on the right. If you have multiple logs on either left or right, you might have to combine them together to get them back to a single log on each side of the equation of the equal sign to enable you to solve for it. Another thing that we need to be mindful of is the restriction that we have on our log or natural log. So the domain for logs and natural logs are all positive real numbers. All right, so our job is when we find our solution, there is a need for us to check our work to make sure that the answer that we found is not an erroneous solution. So we'll kind of, I've talked enough. Let's get into the examples and we will kind of sprinkle all these different techniques and ways to approach a logarithmic equations. All right, so let's look at the first example. In the first example, I have log 3 of 2 minus x is equal to 3. And this setup looks like box 1. The coefficient is 1. So I'm feeling good about myself. I'm able to switch this log equation to an exponential form. So if I do that, it becomes 3 to the cubed is equal to 2 minus x. So I get 27 minus 2 is equal to negative x. X is equal to negative 25. So even though we're saying that the domain of logs are all positive numbers, we cannot dismiss this answer right away because when we plug this in, which we have to, so in checking our work, if I plug in x is equal to negative 25 into the original log expression, all right, not into the simplified exponential function, but into the original, we see that we have log 3 of 2 minus 25, and that is log 3 of 27, which is 3, so that checks out. That's a true statement. You can also look at it from the domain point of view. All right, so if you think about the domain of this expression here, we are saying that 2 minus x has to be greater than 0. We see that we get negative x is greater than negative 2. X is less than 2. Clearly, negative 23 is in that domain. So I'm feeling good about the answer that I found, that the answer has to be x is equal to negative 25. All right, let's look at the next one. In our case over here, we have a natural log. 3x plus 5 is equal to 2. Again, things are looking pretty decent for me. The coefficient is 1, so I'm feeling good. So it kind of looks the same as over here. So if I put down here, if you have ln x, then that is the same as, well, ln x equal to b. That's the same as you doing e to the b is equal to x. So we can also treat the ln the same way too. So again, if I move things to exponential form, this becomes e to the 2 is equal to 3x plus 5. So x is equal to e to the 2 minus 5 divided by 3 is equal to x. So let's go check our work. If we check our work, I'm saying into the original logarithmic expression or equation, we are saying that 3 times e to the squared minus 5 divided by 3, what is that equal to? Oh, I missed. So that plus 5, what is that equal to? So you can see the 3 cancels out. You have ln e squared minus 5 plus 5, which is equal to ln e squared. And one of the properties of logs is we could drop the 2 down. So you got 2 ln e, and ln of e is 1. So we end up with 2, which checks out. All right. You could also find the domain and confirm that answer too. Let's look at the next example. So the next example, I have log 2 of x squared minus x minus 2 is equal to 4. And over here, again, my leading coefficient is 1, so I'm feeling good about myself. And we can solve this pretty easily. So if we move things back into exponential form, I end up getting 2 squared is equal to x squared minus x minus 2. I get 0 is equal to x squared minus x minus 6. Now this is an expression, a quadratic expression that we should be able to solve. So when we solve this, we end up getting x minus 3, x plus 2. So x is equal to 3 and negative 2. So we need to check this. So let's check it. When x is equal to 3, if I plug that into the original expression, we end up with log 2 of 9 minus 3 minus 2, which is log 2 of 4, which is 2. So that checks out. And then in the second one, when x is negative 2, we have log 2 of 4. And then we have plus 2 minus 2. We end up with log 2 of 4, which is 2 again. So both checks out. So the solution to this is x could be 3 or negative 2. All right. Now this presents a different challenge for us because now I see the sum of 2 logs. But the idea is we still got to go back into the box that we looked at. We're still looking at box number 1. But in this case, I have an addition between the 2 logs. So I can fall back onto the properties and ask myself, well, which of the properties allows me to have the sum of the logs? And it's the product. So you need to condense this back into a single log. And to do that, if it's an addition, we are saying that we're looking at log 9 of x minus 5 times x minus 3. And we're saying that should be equal to 1. All right, that should be equal to 1. So in that case, we are back to box 1. I got a log with a base, an argument, and the output is an exponent. So I can easily switch it out to an exponential form. So I end up with 9 to the 1 is equal to x minus 5, x minus 3. Now let's try combine things together. So 9 is equal to x squared minus 8x, and then I get plus 15. So if I keep combining things, I end up with 0 is equal to x squared minus 8x, and then I get plus 6. All right, so if you think about 6, you can't really find any two numbers that multiply to give you 6. Add would give you negative 8, but I do know my quadratic formula. So let's go to the quadratic formula to see if this is going to work out. So x is equal to minus 8 plus or minus negative 8 squared minus 4 1 times 6 all over 2 times 1. So I end up with 8 plus or minus 64 minus 24 all over 2 times 1, which leaves me at 8 plus or minus square root of 40 all over 2, which is the same as 4 plus or minus root 10. So we end up with two values, and our job is to try and test these. So as weird as this number looks like, testing shouldn't be that bad. Okay, so let's see. If we check, so let's check the positive one. We have log 9. So let's do a check over here. Check 9, we got 4 minus plus root 10 minus 5 plus log 9 4 plus root 10 minus 3. Let's see, what does that give us? So we end up with log 9 root 10 minus 1 plus log 9 root 10 plus 1. And let's see what we get over here. So this gives us log 9. And these are differences of each other. So we get 10 minus 1, which is log 9 of 9, which is 1. So that checks out. All right. So this check was for when x was x plus root 10. Now let's do the check for when x is 4 minus root 10. If we do that check, we see that we have log 9 of 4 minus root 10 minus 5 plus log 9 of 4 minus root 10 minus 3. So by inspection, root 10, negative root 10 and negative 5 is a bigger negative number than 4, so we can't have that in there because the domain is supposed to be all positives. Likewise, if I look at 4 minus root 10 minus 3, that's a negative outcome. So we cannot evaluate a negative outcome in that log expression. So this is not the right answer. We have an erroneous solution, which is 4 minus root 10. So my final answer is x is going to be just 4 plus what? Root 10. All right. Any questions. Well, obviously you're online, so let's look at the next question. So the next question again, I'm presented with two logs on the left with a minus sign. So for me to utilize the technique from box number 1, I need to try and combine the terms on the left. So since it's a minus, it's telling me that this is coming from the quotient rule, which means that I can divide 5x plus 1 divided by x minus 1, and that should be equal to 2. So if that's the case, let's solve it out and let's see what we get. So now I'm in a good place to switch to an exponential. So I end up with 5 squared is equal to x plus 1 over x minus 1. I get 25 x minus 1 is equal to x plus 1, which results in is equal to x plus 1. I'm going to get 24x is equal to 26. So x is equal to 13 over 12. So I have this answer here that I need to go and check to see if this is the right answer. Again, I'm plugging this into the original equation. So I got 13 over 12. If I plug that into the original equation, I got log 5 of 13 over 12 plus 1 minus log 5 of 13 over 12 minus 1. And I'm trying to check what the outcome should be. So over here, I end up with log 5. That's 25 over 12 minus, then over here I have log 5 of 1 over 12. All right, so I get a subtraction. If I clean up the work a little bit, I can see that this is the same as log 5 of 25 over 12 divided, so times 12 over 1. We end up with log 5 of 25, which is 2. So indeed, that checks out. Okay. Let's look at the next problem set. So the next problem set, I see that I have terms of logs on the left and 1 log on the right. So it's looking like box number 2, where I have both logs on each side of the equal sign. So my job is, if I can get them all to have 1 single log on the left and 1 single log on the right, then I can extract the argument and work with the argument. So in this case, I have a plus in the middle of the logs on the left. I can combine using the product rule. So the product rule says that this is going to be log x times x minus 1. And that should be equal to log 4x. Since I'm dealing with the same base, I'm just going to take out the argument and set this as x minus 1 is equal to 4x. So I end up with x squared minus x minus 4x is equal to 0. So I end up with x squared minus 5x is equal to 0. So x comes out, I'm left with x minus 5 equal to 0. X is equal to 0 or 5. So I got 2 of them, and here it's a little bit easier because if you recall, the domain for a log expression is anything from 0. So if we do our check and I plug in 0 as one of the solutions, see what happens. I got log 0 plus log 0 minus 1, and then that's equal to log what? 4 times 0. So first of all, I can have a negative, so this is a no-no. Log of 0 It's impossible to get log 0. You can solve this because the domain is x greater than what? Greater than 0. So I can have 0 in there. So x equal to 0 is not a solution. It's one of the Arrhenius solutions in this problem here. But let's check 5. All right, when we check 5, so over here was x is equal to 0. If we check out 5, we have log 5 plus log 4, and that's equal to log 4 times 5. And this is a true statement coming from one of the properties. Okay, so in this case, my only solution here is x is equal to what? X is equal to 5. All right, let's look at the next question. So the next question says 2 times log x is equal to log 2 plus log 3 minus 4. So before we solve the problem, we need to clean up this because it's looking like box example from box number 2 where I have logs on each side. The coefficients are 1. But if I look at the question that I have over here, I got 2 log x. I need to convert that so that the coefficient is back to 1. So that is one of the properties where the power was dropped down. So I'm going to return it back so that I have log x squared. And I'm seeing an addition. I want to try and get it back to a single log. I can multiply the 2 argument, leaving me with 2 times 3x minus 4. Now I'm feeling good about myself because it's of the same base 10. So I can pick the argument and go, I got x squared minus, x squared is equal to 6x minus 8. So if we put things back together, get x squared minus 6x plus 8 is equal to 0. I can come up with 2 numbers that add up to give me 8. Multiply will give me 8. Add will give me negative 6. That's x minus 4 and x minus 2 is equal to 0. So our solution is 4 and 2. So let's go check this to make sure that this is right. So at x equal to 2, you got 2 log 2 is equal to, and again, you got to plug this into the original, okay? So you get log 2 plus log 12 minus, now we're doing 2, so that's 6. So that's 2 times 3 is 6. 6 minus 4 is log 2. So that is that. And that is 2. Okay. So what do we have here? Okay. Oh, I made a little mistake. This is log 2, not base 2. So just log 2 plus log 2. We end up seeing that this is 2 log 2 is the same as 2 log 2. So that checks out. Now let's see the check for x equal to 4. So I end up with 2 log 4, and we're checking to see if that is the same on the left, on the right. So that's log 2 plus, so 4 times 3 is 12. 12 minus 4 is 8. So I'm getting log 8. And let's see if we can clean this up. So 8 is the same as 2 to the third. So this gives me log 2 plus 3 log 2. So it seems like this is giving me 4 log 2. And then on the left side, I can rewrite 4 as 2 log 2 squared. Then I can drop the 2 in front, so I get 4 log 2. So the 2 are equal, so both answers are good. All right, let's look at the next question. So I have on the left, I have an ln, but with an addition. So it's telling me that I can combine those. So that leaves me with x minus 1/2 times 2. And then I need to return this 2 because I want to make sure that I am seeing ln x is equal to ln y. So if I return that, I get ln x squared. And if I clean this up a little bit, I get 2x minus 1 is equal to x squared, ln x squared. Now I can compare and see that I can take the argument 2x minus 1 is equal to x squared. Now I could solve this to get me x squared minus 2x plus 1 equal to 0. That is just x minus 1 squared equal to 0. X is equal to 1. So let's check and see if this is right. So I have ln 1 minus 1/2 plus ln 2, and that's equal to 2 ln 1. Remember that ln 1 is 0, so this is going to 0. Now let's see. I end up with an addition which I can put together as ln, that's, so this is the same as negative, 1/2. All right, so I'm ending up getting 1/2 times 2, which is also ln 1, which is equal to 0. So that also checks out. So I can confidently say that x equal to 1 is the solution. Now let's look at number 9. So number 9, again, I'm still doing the same thing. I just have a whole lot of things to combine. So I'm going to combine the terms on the left to a single log and combine the terms on the right to a single log. So here I end up with log 2 of 3x is equal to log 2 of 5 times x minus 2. Now that I have this, I can apply the rule in box number 2 and go, this is the same as 3x is equal to 5x minus 10. So this gives me negative 2x is equal to negative 10. X is equal to what? X is equal to 5. So here, if we check, we are saying that log 3, 2 of 3 plus log base 2 of 5 is the same as log 2 of 5 plus log 2 of 3. All right, so both answers check out. So the only answer here is that x equal to 5. All right, let's look at the last example. So the last example, I have 2 plus log 2 of x is equal to log 2 of 2x plus 1. So on the left and the right, I'm seeing a log on each side, but I got this 2 bugging it. So I'm going to group everything that has a log on the same side so that I can see that this is 2 is equal to log 2 of 2x plus 1 minus log 2 of x. And then I can combine the terms that is on the right because I see a subtraction which is telling me that this is coming from the quotient, and I can write as a single log 2x plus 1 divided by x. is equal to 2. Now, this is a logarithmic expression from box number 1. So I can switch it to an exponential form, which gives me 2 to the squared is equal to 2x plus 1 all over x, which gives me 4x is equal to 2x plus 1. The 2x is equal to 1, x is equal to 1/2. So let's check to see if this is a true statement. So I got, and I'm plugging into the original, so I got 2 plus log 2 of 1/2 is the same as log 2 of 2 to the 1/2 plus 1. All right, so let's see how this works out. So this is 2 plus, and I can rewrite that as log 2 of 1 minus log 2 of 2. Okay. And then on the other side, I have 1. So I got log 2 of 2, which is equal to, so all this is equal to 1. So let's clean up this side here. Recall that this is equal to 0 plus 2, and then log 2 of 2 is 1, so minus 1. And that's the same as 1. So that checks out. All right, so x equal to 1/2 is equal to, x equal to 1/2 is the solution to the logarithmic equation. So hopefully you've seen the different ways that we are doing this. It's either you can convert it back into exponential, or you have the equivalency of a log equal to a log, and you are taking the argument and setting it equal to each other to try and find the solution, or you are moving things to kind of get things to be in a place where you can switch out from a log expression, a log equation, to a log to an exponential equation. All right, so that is it on logarithmic equation. Hopefully the practice will get you to have a deeper understanding of what we've covered today. Thank you.